Alrighty, let's take a look at web assigns 3 and 4 for electricity. We've got a couple different kinds of questions in here, and in fact, number 4 is about circuits. That's always a big deal. All right, again, a little fuzzy on my end here when I'm looking at the screen. I do have a printout of the homework, so if I do change some of the numbers, I will try to make a note of it for you just so that they're numbers that I can actually see. All right, so let's start with this first one. Potential difference, that is a fancy way of saying voltage. And there it is. We've got a voltage of 120. 120 volts. Power rating is 65 watts. Now, power is one of those things. We know a million different ways to calculate power. Some of our most common, the two that we use the most, are these. Not that there aren't other ones, but there's definitely this one. All right, so if we have power and we have voltage and we're being asked for current, that's a pretty straightforward application. Once we know current and voltage, we can simply use VIR to find resistance. So that it should not be too terribly difficult for you. Okay, the power of a color television. Now this one did throw a few of you for a loop when you were asking me about it. So let's consider we have a power rating of 312 watts, I think, and then we have a voltage of 120. Oh, maybe it wasn't this one because this really does not seem all that tough. When you consider in the last slide, I just told you one of the most common formulas is PIV and we're looking for current. So yeah, that's an easy one. Maybe it's a different one that I'm thinking of here. Let's find out. Let's see. Power applied to a typical. This is the one. Okay, so first of all, let's start with that. Time 1.3. I'm guessing that's a 9. You have to change that to seconds. Not minutes, but to seconds. So again, since converting seems to be one of our weaker areas, shall I say, you just, do I multiply? Do I divide? You always want like a fancy solution to it, man. But you know, sometimes you just got to sit and figure it out. Figure out the units, right? So hours cancels out. What can we change hours to? We can change hours to minutes. We have 60 minutes in 1 hour. What did we do there? We just multiply that, you'll have your number of minutes, but I don't care about minutes, I want seconds. So minutes again has to cancel out down here, and we want seconds on the top. There are, sorry, in 1 minute there are 60 seconds. So basically it is times 3,600, but you do need to change that into seconds. That is important. All right, and don't just try memorizing all the conversions. It's kind of ridiculous. You should be able to convert anything to anything else with a few easy conversion factors without having to say multiply, divide, whatever. And we can always change that. All right, so we're given the power, we're given the voltage, and we're looking for the amount of electrical energy. That's different. And we know the time. However many seconds that turns out to be. Okay, so let's think here. We want change in energy. We've got a couple possibilities here. Power has actually something with change in energy. It is change in energy per unit time. Oh, look at that. We've got this one and we've got this one. I think we have a winner, folks. We can find it pretty quickly with that. You could do some other convoluted stuff with current and power and trying to find coulombs of charge, but hey, if you're all for simple, so am I. All right, that is our easy peasy solution there. All right, let's take a look at number 4. We're looking for energy and power. We're given voltage, and we're given current, and oh, look at that. We've got time again. Again, it's in minutes. We're going to need to change that to seconds, please, before you do anything. But that'll be your time. How much energy does this convert into heat during that time? So energy in joules. We're looking for delta E, then we are looking for power. Okay, power is really straightforward. We can do that one right out of the gate, right? We've got that relationship that we can work with. If we're looking for energy, well, heck, if we have power, the easiest one is right here. Right? If we figure out the second one first, then you can figure out the change in energy very quickly. That's what I would suggest doing. All right, next. Now we're going to start some of the fun circuit stuff. Now, here's my best suggestion for you. Always, 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 always draw a picture. Okay, it gives you a little bit of a clearer picture of what's going on. All right, we got a series circuit here. Here's my battery of 24 volts. Right, and I've got 3 resistors in a series. It doesn't have to be a fancy picture, but it gives you some ideas, right, of what you know the most about. In this case, we've got 4.5 ohms, 7.4 ohms, 11 ohms connected. We want equivalent resistance. That is a fancy way of saying total resistance. And as I'm sure you remember, you simply add them up. All right, that should be an R, and that should be a 3. Hopefully that works out. Determine the current in the circuit. What we know about series circuits is that the current stays the same. So if you've got the total resistance, if you know the total power or the total voltage, you can find the total current. Just use VIR, but make sure you're using all your numbers that are totals. And that would be the current anywhere in the circuit, because that's how series circuits work. Okay, so let's try. I'm trying to scroll through this. It doesn't want to work. Not that one. Let's try 7. There we go. Woohoo! All right, so then we have another one in series, and we're looking to find voltage across the battery. Ooh, tricky. All right, so we only have 2 resistors this time, but I still suggest you draw a picture. I think that's important. Okay, 9.3 ohms, 5.4 ohms. Potential difference on the 5.4 is 12 volts. Label it there. Find the potential difference across the battery. Wouldn't it be nice if it was just 12? Well, too bad. It's just not. So let's consider, what do we know the most about? Well, we know the most about this. Right? We know 2 of the 3 variables for that one out of VIR. So, okay, sorry, that's supposed to be VIR. That doesn't look very IRE. Right, so let's try that again. There we go, a little better. All right, so let's consider. We could figure out the current, couldn't we? Right, what do we know about current in a series circuit? It is the same. So once I know the current on this resistors, I know the current on this resistor. And then if I know the current, then I can do VIR over here, and I will get the voltage on the second resistor. The voltage is going to be the total of the 2, right? So if I take the 12 volts from this one and whatever I figure out for the second one, I've got the total for the whole circuit. So it's a little bit of a backwards way to do it, but we're still using the same principles, and I think it's easier to see what you need to do if you draw the picture and you label everything, because it shows you where your starting point needs to be. So I, again, strongly suggest it every single time. Okay, so now we're going to look at ones that are in parallel. Here we go. I don't know. Does that say 8? I think it does. I think that says 6.5. And the current across the 8 ohm resistor is 0.25 amps. 0.25 amps. Find the potential difference across the battery. Okay, so again, we're looking for this one. If you draw the picture and you label it, you are looking at it going, okay, what do I know the most about? I know the most about the top resistor. I'm going to use V equals IR, and I'm going to multiply these 2 numbers in order to get it. And I'm going to get a voltage, I believe, in this case of 2 volts. What do you know about parallel circuits? Parallel circuits have the same voltage everywhere. So that means this has 2 volts, and that is also 2 volts. I think I might have done that wrong. I think I did the math wrong because I was doing it in my head. So, although maybe I didn't. Maybe I didn't. Maybe that is correct. Anyway, you can check me. Either I multiplied when I should have divided, or I divided when I should have multiplied. But you get the drift. Use Ohm's law at the top. It should match all the other ones. Let's move on. Let's move on, shall we? Mrs. Gray is just going to gloss right over that one. I'm feeling a little sassy today. Okay, so now, oh, there's a chart. How crazy is that? Okay, again, I still suggest, let's draw a picture, shall we? We've got 2 resistors. They are in series, so it's going to look like this. And then let's figure out what we've got. We've got an 18-volt battery, 17.3 ohms here. We've got 11.9 ohms here. Okay, find the current and the potential difference across each resistor. How would I do this? First, I would find the total. I don't know more about either of these resistors. So I would simply add the 2 together, find your total resistance, and then I would use your total voltage to find the total current. Once you have the total current, it's a series circuit. It's the same for both of those. Once you label each of these resistors with the current for each one, you can do V equals IR and figure out the voltage across each resistor. That's the game plan there. All right, what else we got? Oh, just one more left. Oh, it's another chart. This is so crazy. Okay, find the current and position, blah, blah, blah. I think this was exactly the same technique. Again, draw the picture, right? 16.6 ohms, 9.0 ohms, and then 18 volts. I would find, again, I'd find total resistance, add them up, use VIR with the battery voltage to figure out the current. The current is the same across both of those, right? So once you find the current, you found the current for both, then you can do V equals IR on each resistor to figure out the current or the voltage across each. Hopefully this has been helpful. Again, as I always end these with, if you need me, you know where I am. Come ask more questions, bring your work. Talk to you later.